Our next speaker this morning is Jeysen Flores-Velazquez, who comes to us from Cal Poly Pomona, where he's a rising junior this year. He's been working over the summer with Jeff Rich, and he's going to tell us today about localizing the shocks within the interstellar medium of the ongoing merger NGC 3256. Go ahead whenever you're ready.
Thank you, Gwen, for the introduction, and thank you all for joining me here today to hear about my summer research. So let me begin by speaking about the importance of galaxy mergers. Galaxy mergers are a transformative process that may have implications on galaxy evolution. So to further investigate galaxy mergers, I'm taking a look at the galaxy merger NGC 3256. So in previous investigations, utilizing the wide field spectrograph, what was found was that NGC 3256 contains a spectrum of starbursts and shocks. So we would like to expand that work using the Hubble Space Telescope to test the previous analysis and to check whether there are the presence of shocks and starbursts in the interstellar medium. So I'm working with two sets of data, the wide field integral spectrograph and the Hubble Space Telescope. So the wide field integral spectrograph records the spectrum for each pixel of the region that is imaged. And the Hubble Space Telescope has a wide field camera that collects narrowband image data. So we have data for the emission spectra for both sets, for the oxygen 1 line, emission line, oxygen 3, nitrogen 2, sulfur 2, H alpha, and H beta. But unfortunately, the wide field camera 3 captured H alpha and nitrogen 2 at the same time, as you can see in this plot. So the blue demarcation indicates the narrowband filter that captured H alpha and nitrogen 2. So we have to take into account this correction in our BPT diagrams. So previously, when we analyzed the wide field spectrograph data, we plotted the log ratio of O3 and H beta versus the log ratio of sulfur 2 and H alpha. We also plotted the x-axis for log of oxygen 1 versus of oxygen 1 and H alpha. So what these plots allow us to do is search for the shocks in the interstellar medium of NGC 3256. The demarcations you see that are applied from QLI from 2006 allow me to distinguish the ionizing mechanisms present in the interstellar medium. So, excuse me, to the far left corner, we can see that there is a purely H2 region that corresponds to star-forming gas, and above, we have a Seyfert region that corresponds to AGN, any active galactic nuclei that are present, and the bottom right corresponds to the shock emission that we're interested at looking at. So since our Hubble Space Telescope captured H alpha and nitrogen 2 together, we have an issue here. So we have to correct our BPT diagrams and actually take into account the nitrogen 2 that was captured within the narrowband filter. So I produced those similar plots we've seen in the previous slide, but with the sum of H alpha and nitrogen 2. And you can see there's more points as opposed to the previous plots. So we cannot use the demarcations formed by QLI in 2006 to distinguish the ionizing mechanisms of the nebular gas of this galaxy. So we must seek new ways to make cutoffs for these nebular gas demarcations. So we have an empirical method that we applied by taking a look at a galaxy by the name of 17222, which is a purely star-forming galaxy. So the gas that is encompassed in the interstellar medium of 17222 is just purely H2 gas. So I made a cutoff for this sulfur 2 diagnostic diagram, and I made a cutoff at x equals negative 0.28 to discern where the H2 region is located. As you can see in the 17222 plot, most of the H2 gas is to the left of x equals negative 0.28. And I applied that demarcation to my wide field integral spectrograph data, and we can see that it does cut off a few points. So everything to the left of x equals negative 0.28 can correspond to H2 regions for purely star-forming gas, and anything to the right of x equals negative 0.28 can correspond to shocks. But this is just an approximation. We cannot go by this, and we have to search for even more precise ways to make this demarcation. So here we applied it for the oxygen 1 emission line, and we can see similarities in the 172.22 cutoff, but this cutoff is at x equals negative 1.8. So we can see that there's H2 gas in our wide field spectrograph data, and there's shocks. So knowing where these shocks are is important. So we have to now take a look at the Hubble Space Telescope data. And we must first align the image data that is present in our Hubble Space Telescope data to our wide field spectrograph spectrum. And if we align these images together, we get this final aligned image that will allow us to compare the pixels of the Hubble data to the wide field spectrograph data to check whether they're consistent or not. We need to check whether or not the pixel values changed or stayed consistent along the way. So now that we have aligned these two images, we can generate these diagnostic diagrams using the Hubble data. And to my surprise, we found that there's a huge amount of spread in the H beta region, and there's a huge amount of shift in the oxygen 1 region and the H alpha plus N2 region, sorry. So we kind of need to look for a new way to align the data, because we can clearly see there's something wrong in the Hubble data or in the alignment process. The WIVES data looks pretty normal to me, but these reprojections aren't looking quite well. So now we want to see whether or not which points are real in these diagrams. So we want to make signal to noise ratio cuts. So the three images above are for the sulfur 2, the sulfur 2 image of, it's a mask for the sulfur 2 image of the Hubble data. So we made them, and the bottom three images is a mask for the Hubble image of the H alpha plus nitrogen 2 data. So we made these masks to cut off pixel values less than 5, less than 10, and less than 20 to allow us to make a signal to noise cutoff in our diagnostic diagrams. And we applied this cutoff to our log ratio for sulfur 2, and this is the resulting image. So it's still pretty hard to distinguish the shocked regions and the H2 regions. The H2 regions correspond to the dark patches that you see there. The mostly dark patches would be the H2 regions, and anything lighter in between would be the shocked regions. So we kind of see this, and we see that there's mostly shocked regions. So we cannot really discern any demarcation with this image. So now we have to take a look at another method by looking at the velocity dispersions. So using the wide field integral spectrograph data, we made the same diagnostic diagrams, except the y-axis is velocity dispersion. So the right column is for the previous analysis with H alpha alone, and the left column is for the new analysis with H alpha and nitrogen 2 together. And there is a similar trend in both of these plots, that as a velocity dispersion becomes higher, it is more likely to find shocks present in these points of high velocity dispersion. And in these points of low velocity dispersion, they can correlate with H2 regions in the bottom left. So we can use these velocity dispersion maps to make demarcations, which we are looking to make in the future. So for future work, we want to find precise ways to make demarcations for these new diagnostic diagrams involving H alpha and nitrogen 2. And we want to find an effective way to align the Hubble data to the wide field spectrograph data that has less spread, of course. And we want to use the velocity dispersion versus log ratio maps to trace the shock regions as an alternative, just in case the Hubble data doesn't align well with the wide field spectrograph data. And we also are considering looking at models to form precise demarcations to ultimately try to answer the question, how do these shocks impact the interstellar medium of its host galaxy? I would like to take any questions now.
Nice job, Jeysen. Questions for Jeysen on this work?
Jeysen, is there no cube yet from the VLT, from Muse on this galaxy? I thought I had seen one, because if there was one, you could basically just do all the spectral work on a big cube and get the maps without mixing up nitrogen 2 lines and H alpha.
I did not know that. I need to look into that. The Muse cubes, you said?
Yeah, I think you should go into the Muse archive of ESO, which is publicly available, and look for 3256. I may be wrong, but I vaguely remember coming across that it had been observed. I did not look at the cube if it exists.
Okay, thank you. I will look into that.
Other questions for Jeysen?
This is Jorge. Amazing work. This is really difficult stuff to do. I just wanted to mention, if you ever need simulations, you and Rich can come to me. We have a nice suite with fire.
Okay, thank you, Georgia Moreno.
Any other questions for Jeysen? All right, very nice job.
Oh, sorry, can I ask a question?
Go ahead, no, go ahead, Lauren.
I'm always late. That was a very nice talk. Have you thought at all about what kind of models you might use to do the demarcations between the shocks and the H2 regions?
We actually, that was the final step in this summer project. We didn't look at any models, but we considered at the end, because we saw that the Hubble data wasn't aligning well with the wide field spectrograph data. So we're considering to look at models. We don't know which models yet, but we're taking models into consideration.
Very cool, thank you.
All right, I think we should probably move on to the next speaker, but thank you, Jeysen.